In this example, we have two well-insulated rigid tanks shown here, and they're filled with carbon monoxide gas. And the tanks are connected by a valve. So in tank A, over here, we're told that we have, so this is the mass in tank A in the initial state is 1 kilogram. And we're also told the pressure in tank A in the initial state is 100 kilopascals absolute. And the temperature in tank A in the initial state is 300 Kelvin. So we're given that information. For tank B, we're told the mass tank B in the initial state is 5 kilograms. And we're also told the pressure and temperature there in the initial state. So 500 kilopascals absolute and 870 Kelvin. So those are the initial states for tanks A and B. The valve is opened. So this valve is opened, and the contents of the two tanks are allowed to mix until equilibrium is attained. So assuming ideal gas behavior for the carbon monoxide, determine the volume of each tank separately, the final temperature in Kelvin. So since the two tanks mix, they'll have the same final temperature. They'll also have the same final pressure. So we're asked to find that as well. I'm going to assume that any volume contained in this line and valve is very, very small compared to the volume of the tank. So I don't have to worry about the dimensions of that line. Okay, so let me first of all find the volume of each tank. Since I know the pressure and temperature in each tank, and I know that the carbon monoxide is being modeled as an ideal gas, I can then use, and I also know the masses in each tank, I can find the volumes of each tank. So I can use the ideal gas law. I'll just call it IGL. So PV is equal to mRT. That R here is the gas constant for carbon monoxide. I'll come back to that in a moment. But the volume then would just be the mass times the gas constant times the temperature divided by the pressure. Just a note, use an absolute temperature and absolute pressure there since we're using the ideal gas law. And this is the gas constant for carbon monoxide. It's not the universal gas constant. So in order to evaluate this, like I said, I know the mass, I know the temperature, and I know the pressure for each tank initially. I just need to know what the gas constant for for carbon monoxide is. So the way I'm going to do that is I'll just actually calculate it. You could either look it up in a table or calculate it. I'm just going to calculate it. And to do that, I'm going to make use of the fact that the gas constant for carbon monoxide is going to be the universal gas constant divided by the molecular weight of carbon monoxide, where the universal gas constant is 8.314. That's kilojoules per kilomole Kelvin. So that's kilomole Kelvin. And then the molecular weight of carbon monoxide. So the carbon monoxide consists of one atom of carbon and one atom of oxygen. So I could go to the periodic table and look up the molecular mass. We call it molecular weight. It's really kind of molecular mass. I'll use both terms interchangeably, but it's going to be one carbon has a molecular mass of 12.011 kilograms per kilomole. And then one atom of oxygen has a molecular mass of 16.0 kilograms per kilomole. Just out to 2 decimal points. So the molecular mass or molecular weight of carbon monoxide will come out to be 28.011 kilograms per kilomole. So 1 kilomole of molecules of carbon monoxide will weigh just over 28 kilograms. So I can then take that molecular weight, plug it in up here, plug in for my universal gas constant, and then get the gas constant for carbon monoxide. And when you do that, that comes out to be 0.2968 kilojoules per kilogram Kelvin. So now we have everything we need to evaluate the volumes for the initial, for each tank. Okay, so if you do that, the volume of tank A, that'll come out to be 0.890 cubic meters. And the volume for tank B will come out to be 2.582 cubic meters. So there are the volumes of each tank. All right, so now let's determine the final temperature and final pressure. And to determine that, I'm going to make use of the first law. And the reason I think about using the first law here is because, what we have is a before and after event. We've got the before, where we have carbon monoxide, different temperatures, different pressures in each tank. It has a certain amount of internal energy to it. And then the after, the temperatures and pressures will be the same in each tank. We'll have a change potentially in the internal energy occurring. So that, there's a change in the state of the carbon monoxide, before and after this mixing event. During that mixing event, since I know the tank's well insulated, there's no heat transfer. Since the tanks are rigid, I know that there's no pressure work or any other work really occurring in the tanks. Actually, when I say that, I need to identify what my system is. I'm just going to go ahead and make the system both tanks. And so when I look at the first law applied to that system, got the change in total energy of the system is the heat into minus the work done by system on the surroundings. Again, I know there's no heat transfer since it's well insulated. I know there's no work because the tanks are rigid and there's no electricity or rotating shafts or springs or anything like that. The change in the total energy will be the change in the internal energy plus the change in kinetic energy plus the change in potential energy for that whole system. But since the tanks aren't moving, they're not changing velocity, there is no change in kinetic energy, and they're not changing elevation, so there's no change in potential energy. So that means that the change in internal energy for that whole system as we go from before and after is 0. So there is no change in the internal energy of the system. What I need to do then is write out what the internal energy looks like for state 1, that's the before case, and then state 2. So the change in internal energy would be like U2 minus U1, and that's equal to 0. So that means U2 is equal to U1. So let's write down what the internal energy is for both states. Now for the final state, so I'll just write where U2, this is where they both have the same temperature. This is after it's all mixed. So this will be the mass of the carbon monoxide in tank A. I'm just going to write it as MA. That's this value right up here. And then the mass in tank B is right there. That's given. So I'm going to mix these two tanks together so the overall system will have the same mass. We'll have and then this will be multiplied by the specific internal energy at state 2. Remember that we're dealing with an ideal gas. And so the ideal gas, the specific internal energy is just a function only of temperature, right? And so at state 2, since the material in the carbon monoxide in both tanks has the same temperature, they'll have the same specific internal energy, so that's why I can write it like that. I'll come back later to determine what that U2 is. Okay, so that's the specific, that's the internal energy at state 2, and then at state 1, I'm going to have the mass in tank A times the specific internal energy in tank A at state 1, plus the mass in tank B times, I'll put the 1 there just to indicate that this is the before or the initial state. So the mass in tank B times the specific internal energy in tank B in the before state. Okay, and by the way, the mass is up here in this expression. It's just the initial masses adding together, that'll be the final mass. That's just a conservation of mass statement. So for the initial internal energy, it's the mass in tank A times its specific internal energy in the before state plus the mass in tank B times its specific internal energy in the before state. Okay, so those will be the same. So if I plug these expressions up into here, I'm going to get U2, and if I do some rearranging, I'm going to get U2 is equal to M A1 UA1 plus MB1 UB1 divided by MA1 plus MB1. Okay, so now I know the masses because I was given the masses in the problem statement, right? So I know the mass in tank A and I know the mass in tank B. So I know those masses. Now what I need to do is figure out what these internal energies are. So to find those, I'm going to make use of the fact that for an ideal gas, the specific internal energy is a function only of temperature, and I'm given what the initial temperatures are. So I'm going to make use of the ideal gas table for carbon monoxide. So let me go ahead and do that. I've copied over an ideal gas table for carbon monoxide. This comes out of the Moran textbook, the 8th edition. You can see it's table A23. Sorry, the image was kind of a mess when I scanned it. It looks a little warped here, but that's fine. So let's go ahead and look up what the specific internal energies are. So initially, for tank A, the temperature is 300 Kelvin, and tank B, it's 870 Kelvin. So let's go back down here. 300 Kelvin. So that's right here. So for carbon monoxide, the specific internal energy is right there, 6,229 kilojoules per kilomole. So just keep in mind that this is a kilojoules per kilomole measurement. And then 870 Kelvin was the initial temperature for tank B. So again, we go for carbon monoxide over here. That specific internal energy is 18,858. Okay, so let's write those down up here. Just remember those numbers. So UA1 is just U at T1, TA1. And that number we said was 6,229 kilojoules per kilomole. And UB1 is the specific internal energy for temperature TB1. And that one came out to be 18,858 kilojoules per kilomole. All right, let me just double check that. Yeah. Okay, so then we can calculate what U2 is from that. And then U2 comes out to be, when we do the calculation, 16,753 kilojoules per kilomole. All right, so that's the final specific internal energy. It's the same specific internal energy for both tanks since they're at the same temperature. And remember again that we're dealing with an ideal gas, so it's just a function of temperature. So what I need to do now is go back to my table and look up the corresponding temperature for 16,753. So let's look at that, 16,753. And it looks like it's over here between those two values. So it'll be somewhere between a temperature of 780 and 790 Kelvin. It's going to be pretty close to the 780. So remember that our value is 16,753. That's pretty close to the 780 value. So you can do a linear interpolation, and if you do that linear interpolation, it'll come out to be 781 Kelvin. So that's our final temperature. So it's just a matter of using the first law up here and then combining it with the ideal gas table for carbon monoxide. Okay, so the last thing we need to do is find what the pressure is. So to find the pressure, what I'm going to do is make use of the ideal gas law. And the reason I'm doing that is because now I know the temperature, and I also calculated what the volumes of both tanks were. So I know the total volume. So if I have temperature and volume, and I also know the masses, because I'm given the masses up here. So that makes me think of the ideal gas law, because I know PV is equal to MRT. So let me rewrite this. So the mass is just going to be the mass in tank A initially plus the mass in tank B initially. R for carbon monoxide, we already calculated that. Temperature, we just calculated. And the volumes will be the volume for tank A plus the volume for tank B, which we calculated in the very first part of the problem right up here. And so we can go ahead and do those calculations. So when you work out the numbers for that, what you'll get is P2 is 401 kilopascals absolute. All right, so I think that covers everything that we were asked to find. So just to recap this problem, we're dealing with a before and after type of problem where we have some gas in tank A, some gas in tank B. They had different conditions, different initial states. And we were asked to first find the volume. Well, that's just a matter of using the ideal gas law, because we're told to assume that the carbon monoxide has ideal gas behavior. We had to do a little bit of a calculation here to get the gas constant for carbon monoxide, used right there. And this is a nice review of how you get that gas constant using the universal gas constant. It's just the universal gas constant divided by the molecular weight or molecular mass of carbon monoxide. And then to find the final temperature and final pressure, what we did is we applied the first law, recognizing that there's no heat transfer through the walls. The walls are rigid, so there's no work, no pressure work, no electrical work or anything like that. Kinetic and potential energies are different, are zero, because there's no movement or change in elevation. So that means the change in internal energy of the system is zero. And then what we did is we found the internal energy of the system before and after, recognizing that in the after state, the internal energy within the two tanks are going to be the same, so that they just kind of add together. Then we made use of the ideal gas table for carbon monoxide to find what those initial specific internal energies are, just noting that for an ideal gas, that's only a function of temperature. We also used the table to figure out what the temperature was once we had the final specific internal energy. And then we used the ideal gas law once again to find the pressure. So that's a recap. All right, that's everything we need to do, so we'll end the example there.